Hey everybody, this video is going to entail the rest of chapter 8. So we looked at the similarities and differences between solids, liquids, and gases so far. We looked at their intermolecular forces, whether something will experience dispersion, dipole-dipole, or hydrogen bonding. And then we dove into the world of gases. We looked at the ideas of pressure, different pressure units. We looked at STP. So remember, STP stands for standard temperature and pressure, where the standard temperature is 0 degrees Celsius, 273 Kelvin, and the standard pressure is 1 atmosphere. And we looked at the relationship between vapor pressure and altitude and things of that nature. So the remainder of this chapter is looking at something called gas laws, which are looking at various aspects of gases and mathematically looking at their relationships. So as we go through these different gases, you need to be familiar with the name of the law. You need to be familiar with the equation of the law, and you need to know the relationship between the quantities in the laws. So here for Boyle's law, we're looking at a relationship between P, which is pressure, and V, which is volume. Now, as for our units, pressure can be in any unit. We've looked at atmospheres, torr, millimeters of mercury. It doesn't matter what unit it is in as long as we have the same unit on both sides of that equal sign. As for volume, same thing. It can be any volume unit as long as it's the same on both sides. And so we have this equation P1V1 equals P2V2, which is telling us that we have an initial starting set of pressure and volume, and as we change one, the other will change with it. And so we need to know what the relationship is between pressure and volume. And our relationship here is indirect. And what we mean by that is as pressure increases, we're going to see volume decrease, for instance. It can also work vice versa. As pressure decreases, volume will increase. And we see this in everyday life. Think about a balloon, right? If you have a balloon that is blown up and you squeeze that balloon, we're making the volume smaller. And by doing that, we're creating more pressure in the system. And so then we can get to a point where our volume gets small enough and our pressure gets too high that we end up popping that balloon. Now notice here that the volume we're talking about is the volume of whatever the container is that the gas is in. So usually that'll be something like a flask. In lab, we used a graduated cylinder, all of that good stuff. So let's take a look at this example problem and look at what information has been given to us. We're told that a sample of nitrogen has a volume of 478 milliliters and a pressure of 1.03 atm. So those two we know are going to go together because of that and. So then we can see that we are asking what is the new volume if our pressure changes to 0.871 atmospheres and the temperature remains constant. So here we can plug in our information. We know what our P1 is, the 1.03. We know what V1 is, 478. And we know what P2 is, 0.871. And since our pressures are already in the same unit, we know that we don't have to do any kind of special conversions or anything, so we just plug in. So P1 is 1.03. V1 is 478. Again, we don't have to convert that either. So equals, our P2 is 0.871, and we're looking for V2. So take a second, feel free to pause the video, try it out in your calculator, and see what answer you end up getting. And I will do the same. So we're going to start by multiplying the 1.03 and the 478. From there, we can divide by 0.871. And so I end up getting as my V2, 565. And so my unit would be milliliters. And so that would be our final answer. Now, as you're going through, remember your tests are multiple choice. So we can ask ourselves, does this answer make sense? We would think, since the pressure from P1 to P2 is decreasing, that the volume thus has to be increasing because they have an inverse or an indirect relationship. So the fact that our volume did increase means that we're at least on the right track. So if you saw this question on a test and two of your answers are of the volume decreasing, you can automatically cancel those out. You know that that can't be the answer. So that's our first law. This is looking at Boyle. So our second law is looking at Charles' law. And for some reason, this is looking all funky. But you can see the equation. So again, we're looking at the name of the law, which is Charles. You should have the notes with you, so hopefully it doesn't look as funky for you. And we have our equation here. So here we're looking at some division. We have V1 over T1, V2 over T2. So here we're comparing V, which is still volume, and volume again can still be in any unit. And then we have T, which represents our temperature. But temperature specifically has to be in the unit Kelvin. So as a reminder, to go to Kelvin, Kelvin is equal to our degrees C plus 273 or 273.15, whichever way you want to do it. So just bear that in mind. Anytime we are dealing with any gas law, your temperature always has to be in Kelvin. And so it's kind of hard to see here, but it varies linearly. In other words, we have a direct relationship. So as volume increases, temperature increases, and vice versa. Okay, so let's take a look at this question here, and I'll write out the information that we have. So we have a volume. Make sure my colors stay intact. So my volume to start, so V1 is 8.98 liters of hydrogen gas collected at 38.8 degrees C. So my T1 is 38.8 degrees Celsius. And again, you should notice this is in Celsius. We need it to be in Kelvin. So we're going to add 273. So 38.8 plus 273 equals 311.8 Kelvin. We want to know what the new volume will be, so V2, if our new temperature is negative 39.9. So again, we're going to add 273 to that. So negative 39.9 plus 273 gives us 233.1 Kelvin. So now we have all of our information. We're in the correct units. So now we can just go ahead and directly plug in. So I'm going to do that up here. If our volume 1 is 8.98 over 311.8 Kelvin equals, we don't know V2, and we're looking for T2, or sorry, we have T2, which is going to be 233.1. Now, the reason that we have to use Kelvin for temperature here is because there's no such thing as 0 Kelvin. In fact, 0 Kelvin is considered something called absolute zero, which is the coldest temperature possible, and it's so cold that all motion ceases to exist. So we cannot actually achieve 0 Kelvin. They have been able to experimentally get close to it, but it's highly unlikely that we're going to be in a kind of situation where there's 0 Kelvin. But we can have 0 Celsius. But obviously we can't have 0 in a denominator because there's no such thing as dividing by 0. That doesn't exist either. Also, as we can see in this example, we started with a negative value. Now we have all positives, so we don't have to deal with having a negative included. So once we have this information, again, we're just going to do our algebra. So go ahead and pause or try it out. Okay, so at the end, if you wanted, you could do cross multiplication here, or the way that I did it is I started with everything on the left first, and then I multiplied by 233.1 on both sides. And so my final answer for this question then is 6.71, and my unit is going to be liters, since liters was my unit for the other volume. So we've looked at Boyle's law, which compares pressure and volume indirectly. Charles' law, which looks at volume and temperature directly. So then our next one looks at temperature and pressure. And again, I don't know why the screen is looking all funky, but you should have your notes with you that you got in class. So here we're looking at Gay-Lussac's law. Here's our equation. So P1 over T1 equals P2 over T2. And we're going to see that our P again means pressure. That pressure could be in any unit. Our T equals temperature. And again, it has to be in Kelvin. So here, since we're seeing a division again, it looks just like Charles' law, but with pressure instead of volume. So this is again a direct relationship or a linear relationship, which means that as our pressure increases, temperature will increase with it or vice versa. And this makes a lot of sense because think about whenever the weather starts changing and it gets colder. Our temperature decreases, you go to start your car to drive off to school, and it says that your tire pressure is low. So we do see Gay-Lussac's law happening in everyday life as well. So let's write out what information is given to us in this problem. So we're told that we're starting with a temperature of 25 degrees, so that's T1, 25 degrees Celsius, so we can convert that into Kelvin. So add 273, that's going to give us 298. And then our new temperature, so we're told it's going from 25 to 36. So T2 equals 36 degrees C. Again, convert that to Kelvin. So that's going to be 309 Kelvin. And then we're told if the initial pressure, so that means that it's going to be P1, is 3.80 atm, what is going to be our final pressure? So we're looking for P2 here. All right, so again, you're going to set it up exactly like you did with Charles' law. Go ahead and try it out and see if you can get the correct answer. Okay, so once you've finished this up, we should end up with a P2 of 3.94. And again, for our unit, it's going to be the same as our pressure unit was on the other side of the equation. So ATM is our unit. And again, we can ask ourselves, does this make sense? Well, we saw that our temperature went from 25 to 36. So our temperature increases, which means we're expecting our pressure to increase as well. So if it was 3.8, it increased to 3.94. That looks good. Okay. So we can take Boyle's law, Charles' law, and Gay-Lussac's law and put them together to look at all three quantities at once using something called the combined gas law. So here, again, you need to know the name, combined, and we have our fancy equation. Again, it's just all of the equations smushed into one. So I'm going to go ahead and get to a blank whiteboard because, again, it's just hard to see, and I need a little bit more room for this problem. So the question you should still have in front of you from your notes says a sample of methane occupies 2.60 times 10 to the second milliliters. So right off the bat, we know that we have a volume. So 2.6 times 10 to the second milliliters. And we're told that we are at 32 degrees Celsius, so that's a temperature. Again, we know that we need to convert that, so that becomes 305 Kelvin. And that sample of methane is also under a pressure of 0.5 atmospheres. So P1, 0.5. So all of this information goes together. That's how I know it's V1, T1, and P1. So we want to know what would the new temperature be if it now occupies a volume of 5 times 10 to the second milliliters and a pressure, oops, I put V1, P2, of 1.2 times 10 to the third torr. So we look at this information and we say, okay, we're going to have differences in volume, in temperature, and in pressure. That has to be the combined gas law. So we already went ahead and converted our Celsius to Kelvin, but there's one more thing that we need to do. Look at the information that's given to us. Is there anything else that we need to change before we plug into our equation? Hopefully you noticed that our pressure here is atmospheres and our pressure here is torr. Again, it doesn't matter what unit of pressure we have, but they have to be the same. So I'm going to convert my torr into atmosphere, but it doesn't matter if you convert atmosphere to torr, you will still get the same answer for your temperature. So we need to think back to our conversion factor for torr and atmospheres. So we know torr is going to want to go on the bottom to cancel, atmospheres on the top. So go ahead and look up that conversion. Feel free to pause. So you should see that the conversion is 1 atmosphere is equal to 760 torr. So that's going to give us with a P2 of 1.58 ATM. So now, again, we're just going to plug and chug. So P1 is 0.5. Our V1 is 2.6 times 10 to the second. I'm just excluding the extra zeros because I'm going to run out of room. Over our T1, which is 305. equals, so our second P, we changed to 1.58. And our new volume is 5 times 10 to the second milliliters over our new temperature, which we don't know. So that's our unknown. So again, here we're going to do our algebra, do some cross multiplication. So try that out, see if you end up with a value for T2. Okay, when all is said and done, I get a temperature of 1853 Kelvin. Now, if we look back at the question in hand, it says, at what temperature in degrees Celsius? So we always have to go back to the question and figure out what exactly is it asking for. So we need to convert this into Celsius. So go ahead and do that. So it's just the opposite of what we did to get to Kelvin. So we're going to subtract 273 here. And that's going to give us 1580 degrees Celsius as our final answer. All right. So that looks at pressure, volume, and temperature together. But we also know that we're not always dealing with the same amount of substance. So we have another law, which is called the I-gas law, which we already looked at in lab. So let me go back to my slides. All right, and so here is our ideal gas law. So we looked at this before. Again, you need to know the name. This is our equation. So remember in lab, we talked about thinking of it as pivnert so that we can remember that equation. So P here is pressure, but this time we have to be in a specific unit, and that unit is atmospheres. V is volume, and that has to be in liters this time. N represents the number of moles. R is a constant, so it's this number here. This number does not need to be memorized. It is given to you on the exam. So right where you have like Avogadro's number and the periodic table and all of that stuff, you have a value of R. But note that there are two different types of R, and we are only dealing with this one. So make sure that you're looking at these units, or else you might use the wrong value of R. And then T, of course, is our temperature, which we know has to be in Kelvin for all these gas laws. So this is a combination of all the laws that we saw, and including the number of moles or the amount of substance that we have. But why is this called the ideal gas law? What is considered ideal? Well, in order for a gas to be ideal, it has to have something called elastic collisions. And if you've taken a physics class, you've probably heard of elastic collisions before. But an elastic collision is when two substances completely knock into one another and then bounce right off. In other words, when we're looking at an elastic collision, there's no attraction or repulsion between the two substances. Now, normally speaking, there is always some kind of an attraction. We looked at that earlier in the chapter, dipole-dipole, dispersion, or hydrogen bonding. But here we're assuming that there's no attraction or repulsion, they just completely bounce off one another. And then the second thing that we can say makes a gas ideal is that the volume of the particles equals the volume of the container, which we talked about earlier. So we're not looking at the volume of each individual molecule, we're looking at how much space all of those molecules take up because we know that they're constantly in motion anyway. So we can look at this example. At what temperature in Celsius? So we're looking for T, specifically in Celsius. We have 19.4 grams of oxygen with a pressure of 1820 millimeters of mercury and a volume of 5.12 cylinders or liter cylinders. So I'm going to go back to a whiteboard so that we can write this all down. So again, we're looking for temperature, that's our unknown, and we want it specifically in Celsius. We are told that we have 19.4 grams of oxygen. Remember, oxygen is diatomic. Most of the diatomic elements are gases, so you have to make sure that you're remembering that it's O2. Then we have the fact that our pressure is 1820 millimeters of mercury, and our volume is 5.12 liters. All right, so we need to double check, are we in the correct units of things? As of right now, I only see one thing that's in the correct unit, and that's our volume. Volume is already in liters, so that's good to go. We can't have grams, but what can we have? Hopefully you said moles. So we're going to change to moles. We're going to do that conversion. How do we go from grams to moles? Hopefully you just said molar mass. I feel like Dora the Explorer when she's like, where are we going? And then she just looks at you in the TV. So that's how I'm feeling from back here. That's what it's like being a teacher in the era of coronavirus. So 19.4 grams, we're going to use our molar mass to convert into moles. So 1 mole of oxygen will take us 32 grams. So when we do that math, we end up with 0.606 moles. So now we're in the correct unit for amount. While pressure, we're not in the right unit either. We know we don't want to be in millimeters of mercury. We want to be in atmosphere. So we know atmosphere has to go on the top. Millimeters of mercury has to go on the bottom. And so this, remember, millimeters of mercury and torr are the same amount. So we're going to have 1 atmosphere, 760 millimeters of mercury. We do that math, and we end up with 2.39 atmospheres. So now we have all of our information in the correct units. So let's plug it in. So P is 2.39. V is 5.12, N is 0.606, R is a constant, 0.08206 liter atmosphere per mole Kelvin, and T is our unknown. So go ahead and try out the math there and see what value you get for T. Alrighty, so for T, I end up getting 246 Kelvin. But again, the question's asking for Celsius. So we subtract 273, and our new answer, if we take 246 minus 273. I get negative 27 degrees Celsius, and that would be our final answer. So one more law for us to look at. So I'll go back to slides. And so our last types that we're going to look at are Dalton's law. And we looked at Dalton's law in lab. So what this says is that the total pressure of a mixture of gases is equal to the sum of the partial pressures of its components. So the way that we tend to write this is that PT, which stands for the total pressure, is equal to the partial pressure of gas A plus the partial pressure of gas B plus the partial pressure of gas C, etc., depending on how many components there are. So if we think about air, for instance, we could say that the total pressure of air is equal to our partial pressure of nitrogen, and our partial pressure of oxygen, and our partial pressure of the other gases that exist in air. And that's where we get that atmospheric pressure from. So that's our first part. Again, we saw this in lab by saying that the total pressure was equal to the room pressure and the hydrogen pressure, the water vapor pressure. Okay, so that's how we ended up with our P total there. But the question then becomes, well, how do we determine what these partial pressures are? Where do we get those numbers from? And we get those numbers from this equation, which is a little hard to see, so I'm going to rewrite it. But it says PA, which remember is the partial pressure of component A, it can be anything, is equal to PT, which is the total pressure, times, this is actually the Greek letter chi of A. And chi is called the mole fraction. And a mole fraction is exactly what it sounds like. It's the fraction of moles. So chi of A is equal to the moles of that particular component over the total amount of moles. It's just like if we said, let's find the fraction of people in our class that wear glasses. We would count the people that wear glasses, divide by the total number of people. It's the exact same thing here. So let's look at a problem where we have to find the mole fraction of each individual piece in order to find our partial pressures. And so that's what our last problem is here. Determine the partial pressure of each gas in a mixture made of 6 grams of hydrogen, 32 grams of oxygen, 56 grams of nitrogen, and the total pressure of the system is 750 torr. So I'm going to go back to my whiteboard and let's write down what we have. So I'm going to break this down into 3 groups because we have 3 different elements. So we have hydrogen, we have oxygen, and we have nitrogen. So of the hydrogen, we have 6 grams. Of our oxygen, we have 32 grams. And of our nitrogen, we have 56 grams. So we know that in order to determine the partial pressure, we need to know the mole fraction. In order to find the mole fraction, we need to find our moles. So that's going to be our first step. Convert all of these grams into moles. So if we have 6 grams of hydrogen, remember to convert to moles, we need the molar mass. Hydrogen is diatomic, so its mass is going to be around 2.02 or 2.018, whichever way you want to do it. Is 1 mole. For oxygen, again diatomic, so the molar mass is 32 grams per 1 mole. And for nitrogen, we're looking at diatomic, which is going to have a molar mass of 28 grams 1 mole. So 6 divided by 2, that gives us roughly 3 moles of hydrogen. 32 divided by 32 gives us 1 mole of oxygen. And then 56 divided by 28 gives us 2 moles of nitrogen. So to find the partial pressure, we need the mole fraction. So for our mole fraction of hydrogen, we'll do that in a new color. We'll say the mole fraction of hydrogen is equal to the number of moles of hydrogen, which we just found is 3, over the total number of moles. So the total number of moles is going to be 3 plus 1 plus 2, which is 6. So 6 moles total. That's going to give us 0.5. Then we can go over to oxygen. The chi of oxygen is going to be 1 mole over 6 moles. So 1 over 6 equals around 0.167, 0.17, whichever way you want to do it. And then for nitrogen, chi of nitrogen equals 2 moles over 6 moles, which is 1/3, so 0.33 is our mole fraction there. Now we can find our partial pressures. So for our partial pressure of hydrogen, remember we're going to take the total pressure, which we saw from the problem was 750 torr, times the mole fraction, which is 0.5. Now notice that mole fraction does not have a unit because the units cancel out. It's a ratio. So we do 750 times 0.5. That gives us a partial pressure of 375 torr. Then we go to oxygen. Pressure of oxygen is equal to 750 torr times 0.17. And so if I do that, I get 127.5 torr. And then for our partial pressure of nitrogen, we're going to take 750 times 0.33, ran out of space. 750 times 0.33 gives us 247.5 torr. So our final answers for this question would be hydrogen has a partial pressure of 375, oxygen has a partial pressure of 127.5, and nitrogen has a partial pressure of 247.5. And one way that you can check yourself is remember the total pressure, according to Dalton's law, our total pressure should be equal to the pressure of the hydrogen plus the pressure of the oxygen plus the pressure of the nitrogen. So if we take 375 plus 127.5 plus 247.5, we should get real close to 750. Okay, and so that's one way that you can double check yourself. And that is it for gases. So on Monday, we will spend some time going through questions for all of Chapter 8, anything that we kind of have left out. Be on the lookout for new schedule, and we will take it from there. Thanks, everybody.